Hello there, getting ready to jump into some math fundamentals together. Let's do it. Okay, let's first jump in first with some important vocabulary. First things first, you're going to see the word integer a lot. That's any number that doesn't have a fraction or decimal part. So it could be negative, it could be positive, it could be zero, but it won't have any 1/2 or 0.2 or anything like that attached to it. A factor is an integer that can be divided into another integer without a remainder. It's something that can go into another number. So 3 is a factor of 12 because 3 goes into 12 4 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can say the larger number is divisible by the smaller number. So here 12 is divisible by 3 because 3 is a factor of 12. A multiple is an integer that has another integer as a factor. So for example, 12 is a multiple of 3 because 3 is a factor of 12. So you can think factors go in, multiples come out. Some multiples of 5 would be 5, 10, 15, 20, 25, things like that. I want to talk a little bit about terms, variables, constants, and coefficients. And in order to do that, I'm going to use an example. In fact, let me add a little page here so I can have plenty to write upon. Say we were to take this expression, 2x squared plus 5x minus 3. This would be an expression, not an equation. Why? It's an expression because there's no equal sign. There's no way to solve for x here because we don't know what x causes this to be. However, if I do this, now this whole thing would be an equation. Why? It has an equal sign inside it. So that's how we can know it's an equation. The best we can do with expressions is to change their form, but not their values, of course, or pop something in for x to find out what it would equal. Now, each word in an expression is called a term. So if we're looking at this guy over here, each term is held together with a multiplication or division. So this is one term. I'm including the sign in front of it so you can know it's a positive term. That's another term, and that's another term. So here we have 3 terms, and each one of these is a monomial, mono meaning one, monomial. And when you put them all together, they become a polynomial. Monomial meaning one term. Polynomial meaning many terms. Now, a monomial, again, is held together with multiplication or division. So if I go like this, it's a monomial. If I go like this, 2 times x, it's a monomial. If I square the x, 2 times x squared, it's a monomial. It's still a monomial. It's still a monomial. It's still a monomial. It's still a monomial. But the second I take that monomial, duplicate it, put it right down here. Second I take that monomial and I add something to it, now it's a polynomial. Or if I subtract something from it, it's now a polynomial. So monomial versus polynomial, this expression is made up of 1, 2, 3 monomials, and it is itself a polynomial. Now, each of these terms has parts to it. This part right here that has the x in it is called the variable. That's the variable. Why? We don't know what it is, and we can pop in different things for x, so that's the variable. The number part over here, these guys here, are called the numerical coefficient, or just the coefficient. I'll write the whole thing here, but numerical coefficient. The numerical coefficient, or sometimes I'm going to erase it now, is you'll just hear it called the coefficient. That's the number part of the term. You put them together, you get a term. If it has a square in it, it's called a quadratic term. If it has just an x to the 1 in it, it's called the linear term. And if it has no x's at all, like this guy right here, that's going to be our constant term. It's constant. It doesn't change based on what x is. So that's our constant term. Now, speaking of constants, constants are just numbers, but constants can sometimes be represented by letters too, just like variables. So usually constants are represented by A, B, C from the front of the alphabet, and variables are X, Y, Z represented by the back of the alphabet. That's not always true, but usually it's true, and that's why in the problem they'll have to say, oh, these guys are constants and these guys are variables. So just to get clear on the idea of the difference between a constant and a variable, we can think of a familiar equation, y equals mx plus b. This is the equation for a line, right? But the m and the b are constants. These guys are constants. Whereas the x and the y, these guys are variables. So what do we mean by that? We mean that when we're thinking about graphing a line based on this equation, the x and the y will constantly change. We'll input different x's and get out different y's, but what shows the relationship between the x's that we put in and the y's that we get out are things that don't change: the slope and the y-intercept. So say I were to graph a line in this xy coordinate plane, I'll notice that this right here is my y-intercept. So maybe the equation of my line is y equals 2x plus 3. So my y-intercept here would be 3, and my slope would mean I go up 2 over 1 and then put a little point there, right? So that would be a slope of 2 and a y-intercept of 3. Okay, so we'll notice that I still have my x and my y in this equation. I still have my x and my y. Those are my variables. But now I've replaced my m and my b with constants. So anywhere I choose on the line, whether I'm here or here or here or here, my y-intercept is always going to be 3. It's not moving around. It still touches the y-axis right here, no matter which point on the line I'm looking at, right? Same with my slope. No, right here, the instantaneous slope at this point right here is 2. Same here, same here, same here. It doesn't change depending on what input I put in and what output I get out. The slope at this point is still 2. It's constant. Versus this situation, you'll notice if I put a 1 into this equation for my x, if I put a 1 in for my x, in fact, let me just do that. Y equals 2x plus 3. And I'm going to just copy this so we can have it for a second in a minute. So if I put in a 1 for my x, like I have here, I'll get out 5 for my y. So I know the point 1 comma 5 is on my graph. Over 1, up 5, put a point there, that's the point 1, 5. And if I put in a 2 for my x, 2 times 2 is 4, plus 3 is 7. I'll get out a 7 for my y. So put in a 2, get out a 7. That's this point here, 2, 7. Okay, if I put in a 3 for my x, 2 times 3, that's 6, plus 3, that's 9. I'll know the point 3 comma 9 will be on my graph, just like 2 comma 7 was on my graph. So over 3, up 9, put a point here, the point 3, 9 is on my graph. Now you'll notice when I'm here, my x is 1, my y is 5. When I move, that doesn't stay the same. Over here, my x is 2 and my y is 7. And when I move over here, my x is 3 and my y is 9. They change, and depending on what I put in and what I get out. So that's why x and y, we don't fill them in. We leave them as variables so they can describe all the points on this line. Whereas the slope and the y-intercept give us the relationship between those inputs and outputs. So again, the difference between these guys, which are constants, and these guys, which are variables. And we'll see both referred to on this test. So I want to talk a little bit about prime factors. Prime factors are factors of other numbers that are prime. So what's a prime number? Numbers that have exactly 2 factors, 1 and itself. 1 is not a prime number because 1 only has 1 factor, 1. And the only even prime number is 2. because 2 only has the factors 1 and 2, but all other even numbers will also have 2 as a factor. Some other examples of prime numbers are 2, 3, 5, 7, 11, and 13. A lot of people add 9 to the list, but that would be mistaken because 9 has a factor of 3, 1, and 9. That's 3 factors, not 2. Integers can be broken down into factors, and a prime number is the one that can't be broken down into factors. So a prime factor is a factor that can't be broken down into smaller factors. Any number that isn't prime can be reduced to a unique set of prime factors, and all that number's factors are just different combinations of its prime factors. So this can be really helpful in simplifying radicals or factoring. We can even do a technique called making a factor tree in order to find the prime factors. So say I have the number 126. I'm going to break that up into 2 things I know multiply to be 126. It's even, so I know it's divisible by 2, and 2 into 126 is 63. One of these is prime, and when it's prime, I'm going to circle it. 2 is prime, 63 is not. I can break that down a little bit more into 21 and 3. Well, 3 is prime, so I'm going to give it a little circle. 21 is not prime, so I'm going to break it down a little more into its factors, 3 and 7. They multiply together to be 21, and both of those are prime, so I'm going to circle it. So if I wanted to say the prime factorization of 126, I would say it's 2 times 3 times 3 times 7. Prime factorization is just a list of the prime factors. You could also write it as 2 times 3 squared times 7. And basically, 126 is just all those guys multiplied together. If I multiply all these guys together, I get 126. If I multiply different combinations, I'll get the factors of 126. Like 2 times 3 is 6, and 3 times 7 is 21. 6 times 21, that's going to be 126. Or I can combine it a different way. I can say 9 times 14. 9 times 14 will be 126. And so again, we can do this all day long, but it's a fun way to find the factors of something that might be harder to break down if it's a large number. Okay. Decimal places. They will not test you directly on your decimal places. They will not say what number is in the tens place or the tenths place or the hundredths place, but they will ask you to round off to specific digits, so you got to know what they are. The number 2 here is in the tens digit. The number 5 is in the units digit or the units place. Sometimes we call it the ones place, but on this test I'll call it the units digit or the units place. Number 9 is the tenths digit, and it's in the tenths place. And this 7 is the hundredths digit. It's in the hundredths place. So the way to think about this is to say, okay, if I have my spots, my decimal places here, and I have my spots on this side, this right here is our units digit. That's like our ones place. And it's symmetric with respect to this. If I multiply this by 10, this is the tens place. If I multiply it by 10 again, this is the hundreds place. If I go to the left, divide by 10, that's the tenths place. And if I divide by 10 again, that's the hundredths place. So you can see it's symmetrical, except for one multiplies by 10 and the other divides by 10. And again, you might note, if you go one more, 1/1000ths. All right. So keep that in mind for those student-produced responses. If you have to round out to a certain digit, make sure you keep an eye on that. A positive number times a positive number will give you a positive number. A positive times a negative will give you a negative. And because of the commutative property of multiplication, it doesn't really matter what order we do this in. A negative times a positive will also give you a negative. And a negative times a negative will give you a positive. This will be true for multiplying them together, but please remember, say I have 3 and I'm subtracting a -5. These negatives also come together. If you subtract a negative, it really means you're adding a number. So let's talk about fractions. My number one thing about fractions is to remember that you have a calculator. If they ask you to use or add or subtract, multiply, divide by fractions, please definitely drop them into your calculator. I want to talk about them here because eventually we're going to weave them in to working with them in algebra, so knowing how they work is really great. So a fraction is nothing more than one number divided by another number. I can have 3 divided by 4. If I punch that out on my calculator, I'll get the decimal version, 0.75. And to convert a fraction to a decimal, just divide it in your calculator. The top number is called the numerator, and the bottom number is called the denominator. Denominator. When you add or subtract fractions, you have to find a common denominator. The easiest way to find a common denominator is just to multiply the bottoms together. You can't add or subtract fractions that have different numbers on the bottom. This is like saying I have 3 4-size chunks and 2 3-size chunks. How can I make them relate together? They're different sizes. We want to try to get them out of the same size chunks. So if I multiply 4 and 3 together, I get 12. So that's going to be my common denominator. In order to turn a 4 into a 12, I have to multiply the bottom by 3. And in order to do that, I must change the form, but without changing the value. So I'm going to multiply the top by 3 as well, because multiplying by 3 over 3 is equivalent to multiplying by 1. And as you might know, multiplying by 1 keeps things the same. It doesn't change them. So when I multiply the top by 3, I get 9. When I multiply the bottom by 3, I get 12. And 9 over 12 is equivalent to 3 over 4. I'm not changing how much it's worth. I'm just changing the way it looks so it's easier to work with. We can take a look at the other one. If I multiply the bottom here by 4, I must also multiply the top by 4 to keep the same value. 2 times 4, that's 8. 3 times 4, that's 12. And here we can see when we add or subtract fractions, I have 9 12-size pieces, and I'm taking away 8 of those 12-size pieces. That means I will only have 1 12-size piece left. So that you add or subtract the numerators and the denominator stays the same. When we multiply fractions, we simply multiply the tops together and multiply the bottoms together. There's no preparation to do. If I have 2 over 9 times 3 over 4, I multiply the tops together and that goes in the top spot, and then I multiply the bottoms together and that goes in the bottom spot. If you want to reduce fractions, you want to find a common factor, something that goes into both the top and the bottom, and divide. So the top is 6 and the bottom is 36. They're both divisible by 6. So I'll remember if I divide by 6 on the top and 6 on the bottom, that's equivalent to dividing by 1. And dividing by 1 just keeps using the same. So it's changing the form but not the value. Taking the top, the 6, and dividing it by 6. Taking the bottom, dividing it by 6. 6 divided by 6 is 1. 36 divided by 6 is 6. So again, I have something that's equivalent. When we multiply, we can also take out common factors. Say, I'm going to rewrite this because I think I'm going to make it more something you can see in the moment. If we want to multiply fractions, say I have 2 over 9 times 15 over 8, I can go ahead and say, well, when I multiply these together, I'll get 2 times 15 in my numerator and 9 times 8 in the denominator. And if I have something that's a factor of the numerator, of the whole numerator, and something a factor of the whole denominator, I can cancel them out to reduce. So if we think about this, 5 and 9 have a common factor of 3. I could divide them both by 3, right? That would give me 5 here, and that would give me 3 here. Okay, but I could actually do that at this stage over here. I could say this guy's going to end up in the top and this guy's going to end up in the bottom. I can just reduce them here and say, okay, they both have a common factor of 3 that I know is going to cancel out, so that's going to be a 5, and that's going to be a 3. I can do the same with the 8 and the 2. 2 goes into 2 one time, 2 goes into 8 4 times. And now I have something a little bit simpler that I can multiply together. So looking at this here, we multiply the tops together. 1 times 5, that gives me 5, over 3 times 4, that gives me 12. Nice and simple. Now when we divide fractions, we must take the reciprocal of the second fraction and then multiply. I want you to think to yourself, keep it the same, change it to multiplication, and flip. Keep, change, flip. Let's say it together. Keep, change, flip. Yes? So the first fraction we keep the same, 3 over 10. We change the division to multiplication, and then we flip 2 over 5 to 5 over 2. So I want you to notice that dividing by 2 over 5 is the same as multiplying by 5 over 2. Then we can reduce. We can say this 5 is going to cancel out with this 10 because 5 goes into both of them. 5 goes into 5 one time. 5 goes into 10 two times. So now we multiply the tops together, multiply the bottoms together. 1 times 3 is 3, and 2 times 2 is 4. So we'll get 3 over 4. So again, we can think about this. Oh, if I have like 5 and I'm multiplying it by 1/2, well, that's the same, keep, change, flip, as 5 divided by 2. Or if I have 7 over 6 divided by 5 over 1, well, dividing by 5 over 1 is the same as multiplying by, you guessed it, 1 over 5. I'm going to skip this fun trick for fractions. I think, oh, no, I'm not. This is going to be great. If you ever want to combine a fraction with a whole number, remember that any whole number can be written as a fraction. A 3 has an invisible 1 sitting underneath it always. Yes, any whole number does. So if you want to combine them, you can always put it over 1. This works in algebra as well. X is just x over 1. So say, for example, I wanted to say 2 over 3, 2x over 3 plus x. I would just put my x over 1. I would get myself a common denominator. Sorry, that's the world's ugliest 3. That's a 3. What's a common denominator between 1 and 3? Well, it's 3. So I'll multiply the bottom by 3 and multiply the top by 3. And then we can simplify. So this top here becomes 3x. And the bottom here, well, 1 times 3, that's just 3. So I have on the top 3x and on the bottom 3. And then I can add the tops together now that we have a common denominator. And that will give me 5x in the numerator. And the denominator stays the same. We'll put a little 3 down there. So you can see why that would be useful to, if you're combining something, a whole number with a fraction, to put it over 1. When we're multiplying whole numbers by a fraction, this means the whole number can multiply straight across to the numerator, and it can cancel out directly with the denominator of the fraction if we want to. So taking a look at this here, you can think to yourself, is that 7 going to be multiplied by the 3, by the 5, or both? Well, here's your hint. 7 is really 7 over 1. So if I'm just going to multiply it through, like our fraction rules say, I'll multiply the tops together and the bottoms together, so the 7 gets multiplied by the 3, and that invisible 1 gets multiplied by the 5, so our result is 21 over 5. And again, if I wanted to cross cancel, I'd say 3 goes into 9 3 times, 3 goes into 6 2 times, and that simplifies my process because I'll get 3 times 5 on the top and 2 times 1 on the bottom for 15 over 2. Let's skip the TikTok method for adding and subtracting fractions. You guys can ask me about that later. Mixed numbers and improper fractions. When the numerator is larger than the denominator, when the top is bigger than the bottom, that's an improper fraction. There's nothing really improper about it, it's just that the top is bigger than the bottom. A mixed number has a whole number with a fraction part. If you want to turn a mixed number into an improper fraction, you can take that 3 and 1/4, multiply the 3 times the 4, that'll give you 12, and then add on the 1. So we'll say 3 times 4, add on the 1, and then you're going to put it over the denominator of your fraction, which is 4 here. So let's just color code that. 3 gets multiplied by the 4, and then you add on the numerator. And then we put that over the original denominator. Now what we'll get there is 12 plus 1 in the numerator, that's 13, and 4 in the denominator. So 3 and 1/4 is the same as saying 13/4, which makes sense if you think about it, because that 3 is 3 wholes. 3 wholes would be how many fourths? Well, let's see. If I multiply the bottom by 4, I have to multiply the top by 4. So that will give me 12 fourths. Well, that's what we have right here. That's our 12/4. And then we just have to add on that extra 1/4 that we had. So we get 13/4. Really, that same idea that we're just breaking them down into the same size pieces. All right, let's try some. I'm going to pause the video here so we can work through some fractions together. All right, let's jump in with these fractions here. A little fraction practice. Here we see in the first one, we're adding these fractions together. So we need a common denominator. If I multiply 4 and 3 together, I get 12. So I'm going to make that my common denominator. And again, we're going to multiply the bottom here by the opposite guy. 3 and 3 here, so I get 15 in the numerator. If I multiply the bottom by 4, I have to multiply the top by 4. That gives me 40. Here we go. We get 55 over 12. Let's try the next one. Here, the common denominator would actually be 6 because I can just turn 3 into a 6 by multiplying by 2. So that's the least common factor between the both. So let's make them both 6. I don't have to change this one because it's already 5 over 6. Here, if I multiply the bottom by 2 to make the denominator 6, I'll multiply the top by 2, put a little 2 over here, add or subtract the numerators. 2 plus 5 is 7. The denominator stays the same. Now here, I have a mixed number, so I'm going to change that into an improper fraction by taking the 2, multiplying it by the 5, and then adding the numerator 2, putting it all over the denominator. So that's going to give me 12 over 5. So I have 12 over 5 minus 1 over 2. I need to get a common denominator. If I multiply the bottom by 2 here and the bottom by 5 here, I'll have to multiply the top by 5 over here and the top by 2 over here. So our common denominator will be 10. And my numerator over here will be 2 times 12, or 24. My numerator over here will be 1 times 5, which is 5. If I subtract that, I get 19 over 10, and that will be my answer. For our next one here, I'm going to cross cancel. 15 and 3 both have a factor of 3. 3 goes into 3 1 time, and 3 goes into 15 5 times. 7 goes into 7 1 time, and 7 goes into 28 4 times. So we'll multiply the tops together, 4, and multiply the bottoms together, 5. And there we go. Now remember, keep, change, flip. This is a compound fraction and still sphere into the hearts of millions, but we won't worry because that's just 9 over 4 divided by 3 over 10. So if I say keep, change, flip, I'll keep the first one the same. I'll change the division symbol to multiplication, and I'll flip my next guy over there. So what do I get? 90 over 12. Can I reduce that? Sure, I could have cross-canceled here too. That would be a 1. 3 goes into 9 3 times. 2 goes into 4 2 times, and 2 goes into 10 5 times. So that would also give me 15 over 2 and be a quick way to reduce. Please remember, your calculator can also reduce for you. If you have trouble using it, just talk to me and I'll show you how to do it. Now let's hop into our discussion about ratios. A ratio is just a relationship between 2 or more quantities. Ratios are usually expressed as fractions, but there's lots of different ways of describing them. Here we have the ratio of boys to girls is 2:3, or the ratio of boys to girls is 2:3. The ratio of boys to girls is 2/3, or there are 2 boys for every 3 girls. This one is by far my favorite because you can do math on a fraction. Now, I want you to think about the relationship factor here. The idea that if we make a little chart for ourselves, laying out the boys, the girls, and the total. I can spell, I swear. Girls and the total. We said that there were 2 boys, and 2 boys came along with 3 girls. So if I have 2 boys, and they're coming along with 3 girls, 1, 2, 3, we would have them coming along in a little pack of 5. So our total would be 5. Now let's imagine we add 2 more boys to the mix. So now we have 4 boys, and then we add 3 more girls. So we have 6 girls. Our total would now be 10. If we add 2 more boys to our mix, that would be 6 boys total. We add 3 more girls to go along with those 2 boys that we just added. We'll have 9 girls for a total of 6 plus 9, that's 15. Now I want you to notice something. Whenever I do a fraction or a ratio between boys and girls, I get 2 over 3. Boys to girls, 4 over 6. Boys to girls, 6 over 9. What do all of these equal? They all equal 2 over 3, the most reduced version. This gives us amazing predictive power because say I lost track about how many boys I have, but I know I have 51 girls. Well, I know if I put my unknown over the known part, I know it will still equal 2 over 3. So maybe I'll call my unknown x now. X over 51 should still have that same relationship that the boys to girls had before. Now, whenever I have a fraction that equals another fraction like I have here and nothing else is going on, I'm going to do what's called cross multiplying. I'm going to multiply that diagonal together and put it on one side. So that's going to be 2 times 51. And then on the other side, I'll multiply this diagonal, 3 times x. And I'm going to bring down my equal sign. It's an equal sign. So I have this diagonal times this diagonal, and I bring down the equal sign. It kind of looks like a butterfly, yeah? Some people call it the butterfly method. 2 times 51, that's 102, equals 3x. If I divide both sides by 3, I'll find out that x equals 34. And so I just found out what this guy is because 34 out of 51 has the same relationship as 2 over 3. Now, that's a part-to-part relationship. I can also have a part-to-total relationship. Say I didn't know how many girls there were. We'll call that X girls. But I know I have 365 total people. Okay, how can I deal with that? Well, I know that the relationship between part and part is the same. Is the relationship between part and total also the same? Well, let's check it out. Let's check out this one. Let's see. If I do 3 over 5, 3 over 5, or if I do 6 over 10, 6 over 10, if I do 9 over 15, 9 over 15, do all these guys equal the same thing? Yes, they do. They equal 3 over 5. They equal the most reduced version of that ratio. Let me get myself a little bit more space here. And say, okay, well then I know that my x over 365 will also equal 3 over 5. X over 365. And again, I can cross multiply. 5x equals 3 times 365, which is 1,095. If I divide both sides by 5, and of course I'm showing all my work, x equals 219, and that's how many girls I have. So again, gives us amazing predictive power whether we're relating part to part or part to total. So let's look at some practice problems. This is an example of a part to part ratio. A recipe calls for 3 cups of sugar for every 7 cups of flour. If Bill uses 28 cups of flour, how many cups of sugar should he use? How many cups of sugar should he use if he has 28 cups of flour? I think it's really helpful when we're setting up a ratio to kind of put the key in the ignition and say, okay, I know I'm going to have a relationship that equals another relationship. And it's also helpful to set up what you're looking for first. So here I want to know how much sugar when I have 28 cups of flour. Then I can go back to my ratio and see what they gave me. I know I have 3 cups of sugar for every 7 cups of flour. So when I expand the flour, I have to expand the sugar to make sure the relationship stays the same, right? And now I've set it up. You'll notice also that I wrote our units here. Sugar over flour equals sugar over flour. That's to make super duper sure that I am not mixing up what they gave me. So again, just to see for ourselves, if I'm reading this problem, I'm writing down I get 3 sugar for every 7 flour. If I change it for 28 flour, how many cups of sugar should I have? And again, those relationships have to be the same. And once I have a fraction that equals another fraction, we can do what? Cross multiply. So I'll say 7x equals 3 times 28. Divide both sides by 7. I can even just reduce this here. 7 goes into 28 4 times. And so I'll get 3 times 4. That's just a 1 down there, and that's 12. 12 will be my answer. And again, you can always just punch it into your calculator. Now, this one's a little bit different. Let's give this one a read, because this one is part to total relationship. So, a certain part contains only maple and elm trees in a ratio of 2 to 3 respectively. If there's a total of 40 trees, how many maple trees are there in the park? So let's again, we know we're going to set up a ratio because they're giving us those relationships, and they mentioned the word ratio. So let's see what we've got here. We know that we have 2 maple trees to every 3 elm trees. And then it mentions that there are 40 total trees, and we want to know how many are maple. So you'll notice that if I do 2 maples for every 3 elm trees, and then I try to put this total trees somewhere on the other side, if I put it on the top, it doesn't match my maple, so not there. If I put it on the bottom, it doesn't match my elm. Well, I have to put it somewhere, so you know what I'm going to do? I'm going to get rid of my elm here and see if I can't get something from my ratio to match. Well, I know if I have 2 maple trees, I can't draw, so bear with me, and I have, that's an elm tree, just for fun, 3 elm trees, yes? 2 maples and 3 elm trees would mean I have 5 total trees when I have 2 maples. So 2 maples gives us 5 total trees. And then I want to know how many maple I have if I have 40 total trees. Again, this is a great reason to set up what you want first, because look what happens if I set up what I want first. I'd say how many maple out of 40 total trees, and then I can go back to my ratio and grab my maple and grab my what? Oh, I want total. How am I going to get my total? You just add the parts together to get 5 total. Again, either way you set it up, you're going to end up with the same thing. You can see these are the same thing here. So let's cross multiply. Let's take it to the side and cross multiply. We get 5 times x, that's 5x. 2 times 40, that's 80. We bring the equal sign down and into the middle, divide both sides by 5, and we get that x equals 16. And that's our answer. So again, you can see the difference between the part-to-part relationship and the part-to-total relationship for the ratios. So again, anytime they're relating parts together and then kind of like expanding them or contracting them or anything like that, we're going to set up our ratio in this way, a fraction that equals another fraction, and then we cross multiply. Direct and inverse proportions aren't really tested on the SAT math section, but they are really related to what we're talking about, and it comes up sometimes in reading passages. So I wanted to have a quick conversation about this here. So the ratios like we just did are called direct proportions. They mean as one quantity increases, the other one increases. So when we relate them together as a fraction, they always equal the same thing. So saying one quantity varies directly with another means that as one number goes up, the other number goes up. And if we set them up as a fraction, they'll always equal the same thing. Inverse proportion, the variables go in opposite directions. So as one value increases, the other one decreases. So you can say as one goes up, the other goes down. So let's try some of these ratios. Oopsies, so sorry. Bob makes some fruit punch that contains apple juice and mango juice in a 1:5 ratio. If he uses 15 pints of mango juice, how many pints of apple juice will he need? If he uses 15 pints of mango juice, how many pints of apple juice will he need? Let's write this down. We have 1 apple juice to every 5 mango juices. If we use 15 pints of mango juice, we want to know how much apple juice we use. Amazing. We know that these relationships are the same. How much apple juice for 15 mango juice? Well, we use 1 apple for every 5 mango. So now we have our relationship and we can cross multiply. We will take 5x equals 15, divide both sides by 5, and we get that x equals 3. In an animal shelter, we have 2 cats for every 3 dogs. If there are 45 animals, ooh, this is a part to total. We find it out right here because they didn't say cats or dogs. They didn't say our parts. They said the total. How many dogs are there? So let's set up what we want first. How many dogs when there are 45 total animals? Yes? Let's go back to our ratio over here. How many dogs do we have? We have 3 dogs. How many total do we have? Well, 3 dogs come along with 2 cats. Our total would be 2 plus 3. So that's 5 total. I'm going to put that in the denominator. And now we can cross multiply. We have 5 times x. That'll give us 5x. And that will equal 3 times 45. 3 times 45, that's 135. And when we divide both sides by 5, we get that x equals 27, 27 dogs. Let's look at our next one. Asif's library has 3 hardcover books for every 8 paperback books. If he has 121 books in his library, how many of them are paperbacks? Well, 121, that's a total. That's a total, so let's set up what we want first. How many paperbacks if we have 121 total books? Let's go back to our ratio. How many paperbacks? We have 8 paperbacks. How many total do we have? Well, if we have 3 hardcover that come along with our paperbacks, we will end up with 11 total books if we have 8 paperbacks, so 11 total. We can cross multiply, so we get 11x equals 8 times 121. Which is 968. If we divide both sides by 11, we get that x equals 88. And that's our answer, 88 paperback books. At a certain school, the ratio of boys to girls in 7th grade is 3 to 5. If there's a total of 56 7th graders, how many of them are girls? Let's set up what we want first. How many girls out of 56 total 7th graders? Let's go to our ratio. How many girls? We have 5 girls. And 7th graders, we have total here. How many total do we have? Well, 5 girls come along with 3 boys. There will be 8 total. 5 plus 3 is 8. And let's cross multiply. 8 times x is 8x. 5 times 56. 5 times 56 is 280. If we divide both sides by 8, we'll get 35. There are 35 girls. All right, let's move on to our next topic, rates and units. Rates and units. So we can use rates and units to do unit conversions, basically to convert from one form to another form without changing the values. This can be very intuitive. We can just, be like 3 feet. So if I'm looking for how many inches are in 3 feet, and I know that each foot is 12 inches, we could just multiply 3 feet times 12. But we can also set it up as a multiplication of fractions. I can say, okay, I have 3 feet. If I multiply this by this relationship, 12 inches over 1 foot, what I'll notice is that my feet as units, one's on top, one's on bottom, they'll cancel out. If I multiply the tops together, I'll get 3 times 12, which is 36 inches over 1 with no units, which is just 36 inches. You might be familiar with this for dimensional analysis in chemistry or physics, how units can cancel each other out. But just to get a more intuitive sense of what these conversion factors are doing, I want you to think about the idea that if I put x equals x on my paper, I think we can all agree that x can equal x. X is x. Now, if I divide both sides by x, assuming that x is not 0, this side will reduce anything over itself equals 1. So I can say if I take 2 things that equal each other and put one over the other, it'll equal 1. And then I can go ahead and multiply by it to change form but not value. So let's see that over here. It says that 1 foot equals 12 inches. So if I divide both sides by 12 inches, the 12s will cancel out. It'll become 1s. Inches will cancel out. And I'll just be left with 1 on this side. So I'll find out that 1 foot, sorry for my handwriting, 1 foot and 12 inches equal 1 foot divided by 12 inches equals 1. So it's a way for me to take 3 feet and multiply it by essentially 1 to adjust my units. So again, if I multiply the numerators together, I'll get 36 feet inches. If I bring my units along with me, over 1 foot. The feet will cancel each other out, and I'll be left with my value, but now in inches. So it's almost like a little hack to help you track your work and know what you should do next. So let's look at some more of these. What if I wanted to say how many seconds are there in 2 days? Basically what I want to convert here is 2 days into seconds. So 2 days, I want to turn that into how many seconds? Okay, let's think about this for a second. Days into seconds. Well, I don't know how many seconds are even in 1 day. I know how many seconds are in a minute though, so I can give myself that relationship. 60 seconds is equivalent to 1 minute. So if I put one over the other, what I've just made here, we'll call it a conversion factor, something I can multiply by to change the units. Now, I'm getting closer to days, but I'm not there yet. I can list another one. I can say that I have 60 minutes in 1 hour. That's another conversion factor. I can also say I have 24 hours in 1 day. So all these things are going to be equal to 1, so I can multiply them to change my units. Now let's color code them so we can see how this works. I'll make the first one green, and then blue, not blue, that's yellow. Let's make the last one blue and say to ourselves, okay, if I'm starting this journey with 2 days, and remember, we can always think of a whole number over 1, right? Which color will help me cancel out days? Well, I need one with days in it to help it cancel out. So I'll put that right next door here. And I'm gonna make sure I put my days on the bottom. I could invert it too, because if I swapped it and said 1 day over 24 hours, it would still equal 1. So if I need to swap it, I totally can, but right now I don't. Okay, don't need to swap the top and the bottom. So now look what happens to my units. I have days on top and days on bottom. They're gonna cancel each other out, and I'm left with how many hours there are in 2 days. And again, this might make intuitive sense. Every 2 days, every day you have 24 hours, so 2 times 24 makes sense that would be the number of hours in 2 days. So now I'm left with hours, but I didn't want to be left with hours. I wanted to be left with seconds. So we already used our blue one. What else can we use now? How about our yellow one? That has hours in it on the denominator. That will help us cancel out our hours in our numerator. So we'll write 60 minutes in 1 hour. Okay, now our hours are going to cancel each other out. And I'm left with minutes, but wait a minute. I didn't want to be left with minutes. I wanted to be left with seconds. So I'll use my last conversion factor that has 1 minute in it to cancel out my minutes and get the number of seconds. 60 seconds in 1 minute. Now again, you'll see my minutes cancel each other out. One's in the numerator, one's in the denominator. And this is how you know you did it right. We are left with the units that we wanted in the question. We wanted to know how many seconds, and that's the units we're left with. Now all we have to do, using our fraction rules, is multiply the tops together, and we'll get 172,800 seconds. And in the denominator, just 1 times 1 times 1 times 1, that's just going to give us a 1 in the denominator. So we end up with 172,800 seconds as our answer. And again, the technique for this, write down your conversion factors and then see what you have and what you want. Turn what you have into what you want using your conversion factors. So it's even more fun the more complicated it gets, and we can let our units help us. Here's this problem says, a sample of oak has a density, that's our density, of 807 kilograms per, which means divide, cubic meter. It's tempting to write cm for that, but that's centimeters. What we mean by cubic meter is meters cubed. So it's 807 kilograms per 1 meter cubed. The sample is in the shape of a cube where each edge, so let me draw a little cube here for us, where each edge has a length of 0.90 meters. To the nearest whole number, what is the mass? We want the mass in kilograms. We want our answer in kilograms of this sample. Well, I can't really see how these are going to play nicely together. This is in meters. This is in kilograms per meters cubed. Meters cubed, I have meters, and meters cubed don't play nicely together. But I wonder, can I help them to play nicely together? Well, sure. If I cube this value here, I will find the volume of this solid. So again, I'm using my units to help me. I want meters cubed so it'll play nicely with my conversion factor. So I'm going to take this and I'm going to cube it. And when I cube the whole thing, the units will get cubed as well. So I'm going to take my calculator and take 0.9 and cube it. And I'm going to get 0.729 meters cubed. I can then take that value, 0.729 meters cubed, and multiply that by 807 kilograms over 1 meter cubed. And what's going to happen to my meters cubed now? They're going to cancel each other out, and we're going to be left with just our numerators multiplied together and our answer in kilograms. 0.729 times 807 gives us 588.303. Sorry, getting a little squish there. And that's closest to 588. The same principle applies to questions with rates. We have here, Molly can bake 3 pies in 2 hours. How many pies can she bake in 10 hours? So again, we could set this up as a ratio, 3 pies in 2 hours. How many pies in 10 hours? And we can cross multiply. Or we can say, listen, in 10 hours, I want to convert that to a number of pies. I know I have 10 hours, and I want to know how many pies. This can be set up as a conversion factor. A rate, it can be a conversion factor. That's 3 pies in 2 hours. And notice if I put this right here, 3 pies in 2 hours, what happens to my hours? This is over 1. The hours will cancel, and I find out that I get 30 over 2 pies, or 15 pies in 10 hours. So again, it's all about looking for those conversion factors and looking what you can cancel out. So let's try another one. Pure beeswax has a density of 0.555 ounces per inches cubed. It says cubic inch, but remember, inches cubed. An online company sells pure beeswax at a price of $8 per 1 ounce. What is the selling price in dollars per cubic inch for pure beeswax from this company? And again, I want it in dollars per cubic inch. I want dollars on the top and cubic inch on the bottom, 1 cubic inch on the bottom. Who don't I want? I don't want my ounces. So what will I do? What's going to happen if I just multiply these guys together? Let's do it to the left. Let's see what happens. My ounces cancel out, and in the numerator, I'm left with 0.555 times 8. And my units are still in dollars. That's what I'm left with in the top. And on the bottom, 1 inches cubed times 1. And no ounces because those canceled out. Tell me, are we left with the units that we wanted? Are we left with dollars per cubic inch? Absolutely. So we can multiply our tops together and multiply our bottoms together. 0.555 times 8 equals $4.44 per 1 times 1. That's just 1 cubic inch. So our answer to this question would be 4.44. And we would grid it in like that, just like that, without the dollar sign. Remember, we don't ever try to grid in a dollar sign. So our answer that we would put in our little student-produced response area would be 4.44. So let's try some. Mark can eat 20 hot dogs in 4 minutes. So I'm going to write 20 hot dogs in 4 minutes. That's a rate, so I can use that as a conversion factor. How many hot dogs can he eat in 5 hours? Well, I know I have 5 hours, and I want to convert that to a number of hot dogs. So I'm going to take 5 hours, and I'm going to say, wait a minute, I don't have anything to cancel out hours. I just have minutes. So let me add another conversion factor here. I know 60 minutes is 1 hour, and now that I can use to cancel it out. So let me take this conversion factor, and I'm going to multiply it by my 5 hours. Looks what happens to my hours by hours, and I'm left with a number of minutes. Now I need to cancel out those minutes to get a number of hot dogs, so I'll take my other conversion factor. I'll move it right over there. Let me move this all over a little bit more, and you'll notice what happens here. My minutes cancel each other out as well. And what am I left with? Multiply my tops together, multiply my bottoms together. 5 times 60 times 20 hot dogs in my numerator, and just 1 times 4 in my denominator, which leaves me with 5 times 60 times 20. That's going to be 6,000. Is that right? Yeah, 6,000 hot dogs. Divided by 4, 6,000 divided by 4 is 1,500 hot dogs. Whew, that's a lot of hot dogs. All right. For the next guy, Elizabeth jogs 2 hours each day, 2 hours in 1 day. Her average jogging speed is 4 miles per hour, per 1 hour. If she jogs 5 days in 1 week, how far will she jog over 3 weeks? We want a distance when we know she's going 3 weeks. So let's put 3 weeks on our paper. Let's see what will help us cancel out weeks. So we have our conversion factor right here. Yes? Let's see if I can keep that line. Let's move that over to multiply by our number of weeks. Oopsies. Let's move that over. Technical failure. There we go. Move that over here and say, all right, if I multiply these together, will my units cancel out? Let's put weeks over 1. Absolutely they do, and I'll be left with a number of days, but I didn't want days. I wanted how far, so let me grab my conversion factor that has days in it and move that over here. Let's multiply them together. We'll cancel out our days, and we'll be left with hours. I didn't want hours. I wanted miles, so let's take my conversion factor that has miles. Let's pop it in right there. And we'll say, oh, our hours cancel out. And we'll be left with multiplying our numerators together. 3 times 5 times 2 times 4 miles over 1 times 1 times 1 times 1. Well, that's just 1. And what will I get? Let's look at our numerator. 3 times 5 times 2 times 4 is going to leave us with 120 miles over 1, so I'm not even going to write it. That's our answer, 120 miles. If a car is traveling at a speed of 90 kilometers per 1 hour, how fast is it traveling in meters per second? Ooh, I see they said second, right? But we want meters per second. I have hours, so I know I want the conversion factor of 60 seconds in 1 minute. And I got to get to hours, so I also know I have 60 minutes in 1 hour. And they give me this conversion factor, so I bet you I'm going to use it, that we have 1 kilometer per 1,000 meters. Okay, let's take what we're starting with and see if we can't get some stuff to cancel out. So to cancel out hours, I'm going to grab my second conversion factor and put it right next door. And then that's going to cancel out my hours, is it? No, oh no, do you see they're both on the bottom? They're not going to cancel. What will I do? I will flip it. I'll flip the top and the bottom. I'm going to take the hours and put that on the top, and I'm going to take the minutes and put that on the bottom. And am I allowed to do that? Absolutely, because same over same, if you flip it, still equals 1. So let's cancel out our hours. Whew, okay, that's looking good. Now I have minutes, but I didn't want minutes. I wanted seconds. So let me grab my other conversion factor. Can I put it in like this? Oh no, do you see we have both of our minutes in the denominator? That's not good. We need them to cancel. We need to swap them. So let's go ahead and swap them. Put this guy up top. Let's put this guy on the bottom. Okay, good swap. Let's see. Is it going to cancel? My minutes on the bottom cancel with my minutes on the top. Good to go. All right, let's see. Let's bring in that last conversion factor. Because at this point, I have my seconds in the denominator where I wanted them to be. I wanted per second, so I have that. But because of the commutative property of multiplication, I can multiply way over here and still cancel out something over here. But look, do you see how our kilometers are both in the numerator? This is no good. I need to swap my last conversion factor to put my kilometers in the denominator. So let's do that real quick. I'm going to put 1 kilometer in the denominator and my 100 or 1,000 meters in my numerator. Now, my kilometer over here, when it's in the numerator, will cancel out my kilometer over here. If it makes you feel more comfortable, because we can really put this in wherever we want, we can have this over here as well to see that they cancel out. Again, commutative property of multiplication. I can put it wherever I want. So when we multiply the tops together, multiply the bottoms together, what are we left with on the top? We have 90 times 1 times 1 times 1,000 meters over 1 times 60 times 60 times 1 seconds in the denominator. Oh my goodness, I absolutely have the units that I wanted. So let's punch this out on our calculators. 90 times 1 times 1 times 1,000. That's going to be 90,000 meters divided by 60 times 60. So 90,000 divided by 60 times 60, and that's going to give us 25. So, sorry, 3,600 here seconds, and that's going to give us 25 meters per second. All right. A town is painting parking spots along the curb of its street. Each spot must be 20 feet long. I know it doesn't sound like a rate, but we'll write that down. One spot is 20 feet long, and each block, one block, is 300 feet long. What is the maximum number of parking spots? We're looking for number of parking spots that can fit on one side of a street that's 4 blocks long. So 4 blocks long, I want to turn into the number of parking spots. So let's start with 4 blocks. And let's grab our conversion factor. Ooh, that guy's no good. It's upside down because that blocks is in the numerator. If this blocks is in the numerator, I need this block to be in the denominator. So let's flip it. 300 feet in 1 block. Now check it out. My blocks will cancel out. Bye-bye. Yes? I'm left with feet. I didn't want feet. I wanted spots. So can I put in my conversion factor just like I have it here? Absolutely. Feet are in the denominator. 20 feet in 1 spot. So again, we could spend a bunch of time and energy thinking whether we wanted to multiply or divide by that 20. But if you use your conversion factors, if you're focusing on your units, it'll tell you you need to divide. So we can cancel these guys out. All right, we'll multiply our tops together, multiply our bottoms together. We got 4 times 300 times 1 in our numerator, number of spots, divided by 1 times 20 in our denominator. That gives us 1,200 spots divided by 20, which leaves us with 60 spots. All right, this last one's a doozy. Hang in there with me. Mark can eat 20 hot dogs in 4 minutes. Hot dogs are sold in packages containing 12 hot dogs in 1 package. Packages cost $6 each, so it's $6 for every 1 package. How much money will it cost if Mark buys enough hot dogs to eat for 3 hours continuously? So I want to know how much money comes from 3 hours. So I want to convert my 3 hours and turn it into an amount of money. So I'll know I have the right answer if my units say monies at the end. All right. How do I cancel out hours? I have nothing, but I do have minutes. So it means I need one more conversion factor. 60 minutes in 1 hour. Okay, let's use that. Let's take that conversion factor and pop it in right here. 60 minutes in 1 hour. My hours cancel out. I'm left with minutes. Let me grab my conversion factor with minutes. Minutes is in the numerator, so I want to make sure my conversion factor has minutes in the denominator. That's 20 hot dogs in 4 minutes. Minutes are going to cancel out. Bye-bye, minutes. And I'm left with, I forgot to cross out my hours over here. This cancels with this, and this cancels with this. I'm left with number of hot dogs. Now I've already used this conversion factor. I have hot dogs. I need to cancel out hot dogs. So this is my other conversion factor with hot dogs, but I need to invert it because now they're both in the numerator. I have hot dogs in the numerator here and here, but I need one on top, one on bottom. So let's invert our conversion factor. And we'll put one package has 12 hot dogs. My hot dogs are going to cancel each other out by hot dogs, and I'm left with a package. Now, wait a minute. Package, I need to cancel that out. I need money, so I'm going to use my last conversion factor. That's $6 for one package. Now, my package is one in the numerator, one in the denominator. Will cancel each other out. And am I left with the amount of money that I wanted? Absolutely, I am. Check it out. That's the right unit. So we'll multiply our tops together, multiply our bottoms together. For fun here, let's just do a little cross-canceling. 12 goes into 60. Let's see how many times. 12 goes into 60. Does anybody know? 5 times. So that'll turn into a 1. That'll turn into a 5. I can cancel out my 4 and 20. That could be a 1, and that could be a 5. 4 goes into 4 one time. 4 goes into 25 times. And now I have all ones in my denominator, which makes my life a little easier. So in my numerator, I just multiply 3 times 5 times 5 times 1 times 6. And in the denominator, I just have 1, and I know that's an amount of dollars. So I'm going to grab my calculator. 3 times 5 times 5 times 1 times 6. And I'm going to get $450 is my answer. So listen, that's plenty of torture for the moment. So let's pause here, and we can pick this up in our next video.